Imagine you have a magic box that can make anything you ask for. You ask it for an apple, and inside, an apple appears. You ask for a pencil, and there it is. You could ask for almost anything, and the box would make it. But this box has one very strange rule. It does not decide what is inside until the moment you open it and look. Until you look, everything you could have asked for is somehow in there at once. Every possibility, all together, and only in the instant you lift the lid does the box finally choose and become one single thing. Now, that sounds like a fairy tale, a children's story, but here is what should stop you cold. This is almost exactly how the smallest pieces of our universe actually behave. A particle, when nobody is watching it, is not in one place. It is in many places, in many states, all at once. And the moment someone looks at it, measures it, touches it, it collapses into just one. And this is not a trick, or a guess, or a piece of philosophy. It has been tested in real laboratories again and again. And in the year 2022, 3 scientists won the Nobel Prize in physics for proving something almost impossible to accept. That reality, at its deepest level, is simply not what we always believed it to be. This question is so unsettling that it robbed the greatest minds in history of their sleep for 100 years. Even Albert Einstein could not make peace with it. He once asked, almost in frustration, "Do you really believe the moon is not there when you are not looking at it?" He spent the last decades of his life certain that the strangeness had to be an illusion, and, as we will see, one of the most careful experiments ever performed would eventually prove him wrong. So tonight, we are going to climb inside that magic box. We are going to travel down to the smallest level of reality that exists, the level where every rule you trust, every instinct you have about how the world works, quietly falls apart. We will see how a single particle can be in 2 places at once. We will meet a cat that is somehow alive and dead at the same time. We will follow Einstein into the fight of his life. And we will arrive at a question so deep that it may change how you see your own place in the universe. But first, my one honest promise, the same one I always make. Some of what you will hear tonight is settled, proven science, confirmed beyond any doubt, and some of it is still a mystery that even the greatest physicists alive cannot agree on. And every single time we cross from what we know into what we only wonder, I will stop and I will tell you plainly. And before we begin, one small thing. I have noticed that many of you come back for these journeys but have not yet subscribed. If you would like to keep exploring the deepest questions in all of science with us every Wednesday and Sunday, just subscribe and turn on the bell so the next one finds you. Now, settle in, let the day fall away, and let us open the box. So before we can understand how strange the universe gets, we have to ask a simple question. What is everything actually made of? You, the chair you are sitting on, the air, the stars. What are the building blocks? Humans have asked this for thousands of years. The ancient Greeks had a beautiful guess. They imagined that if you took any object and cut it in half, then in half again, and kept going, you would eventually reach a piece so small it could not be cut any further. They called that final, uncuttable piece the atom, which simply meant unsplittable, and they were remarkably close to the truth. Because everything really is made of atoms. Every object you have ever touched is a vast collection of them. To give you a sense of how small they are, consider this. In a single drop of water, there are more atoms than there are stars in the entire observable universe. That is not a poetic exaggeration, it is literally true. The small hides numbers just as staggering as the vast. But here is where the Greeks were wrong. The atom is not the smallest thing. It can be split, because an atom is itself made of smaller pieces. At its center sits a dense core called the nucleus, packed with 2 kinds of particles, protons and neutrons. And around that core, whizzing about, are tiny particles called electrons. Now let me show you something that will change how you picture solid matter forever. An atom is almost entirely empty space. The nucleus at the center holds nearly all the weight, but it is unimaginably tiny compared to the whole atom. If you blew up a single atom to the size of a football stadium, the nucleus at its center would be no bigger than a pea sitting on the 50-yard line, and the electrons would be like specks of dust drifting somewhere up in the highest seats. Everything in between, the entire stadium, would be empty. Think about what that means. The chair beneath you, which feels perfectly solid, is almost entirely nothing. You yourself are almost entirely empty space. The solidness you feel your whole life is an illusion, created by invisible forces between these tiny specks. What we call solid matter is really a ghost, mostly made of emptiness. Now, back to those protons in the nucleus. Because they hide one of the most elegant secrets in all of nature, the number of protons in an atom decides what that atom actually is. That single number is the entire identity of an element. Let me show you how powerful this is. Take an atom with 79 protons in its nucleus. That atom is gold. Now imagine you could reach in and remove just one proton, leaving 78. It would no longer be gold at all. It would instantly become platinum, a completely different metal. Add protons instead until you reach 82, and now you are holding lead. Gold, platinum, lead, three utterly different materials, and the only difference between them is how many protons sit in the core. Change the count by one, and you change the very substance. For centuries, alchemists dreamed of turning lead into gold, and everyone laughed at them as fools chasing magic. But it turns out they were not entirely wrong. They were only aiming at the wrong target. The difference between lead and gold is real, and it is tiny. It is just 3 protons. They simply had no way to move them. So all the astonishing variety of the world, every metal, every gas, every material in your body and in the stars, comes down to nothing more than how many protons are stacked in a nucleus. It is the universe playing an endless game with a single number. But we are not at the bottom yet, because even protons and neutrons are not the smallest things. Zoom in on a single proton, and you find it too is made of still tinier pieces, particles called quarks. And here, at this deepest level, at the scale of quarks and electrons, the ground finally gives way beneath us. Because when you look this closely at reality, every comfortable rule you have ever known simply stops working. Things no longer sit in one place. Cause and effect begin to blur, and certainty itself dissolves into something far stranger. That is where we go next. So let us step down into that deepest level and watch the rules fall apart. In the world you live in, everything is predictable, and this predictability is the bedrock of everyday life. If you throw a ball, you know roughly where it will land. If you know how hard you threw it and at what angle, you could calculate the exact spot it will touch the ground. Drop a glass and it falls. Every single time, the big world runs on cause and effect. One thing leads to the next, cleanly, reliably. This is the world our minds were built to understand. For centuries, scientists believed the entire universe worked this way, all the way down. They imagined that if you knew the position and motion of every particle in existence, you could predict the whole future perfectly, like a giant clockwork machine ticking forward, everything determined, everything knowable. It was a comforting picture. And then we looked closely at a single particle, and that comforting picture shattered completely. Because in the quantum world, at the scale of electrons and quarks, cause and effect stop being reliable. You cannot say where a particle will be. You can only say where it will probably be. Not because you lack a good enough instrument, not because your measurements are sloppy, but because the particle itself does not have one definite answer. Uncertainty is not a flaw in our knowledge. It is built into the fabric of reality. Let me make this concrete. Imagine you throw a ball in your room, and instead of landing in one spot, it could land anywhere. Sometimes here, sometimes there, sometimes in the far corner. And the only thing you could ever say is that it has a 70% chance of landing near the middle and a 30% chance of landing by the wall. You could never say for certain where it would go. You could only ever speak in odds. In the world you know, that sounds insane, but at the level of particles, that is simply how things are. This is why scientists stopped drawing electrons as tiny balls orbiting a nucleus, like planets around a sun. That neat picture, the one in every old textbook, is wrong, because an electron does not travel in a clean, predictable orbit. Instead, physicists draw something called a cloud, a fuzzy, blurry haze around the nucleus, and that cloud is not the electron's body, it is a map of probability. The cloud is thickest where the electron is most likely to be found, and thinnest where it is least likely. The electron is not smeared out like a fog. It is simply everywhere it could be, all at once, until something forces it to pick a spot. Think about how strange that truly is. We have a particle with no fixed location, a thing that exists only as a set of possibilities, a range of maybes until the moment we check. It has traded certainty for chance, and the universe, at its deepest level, does not deal in facts, it deals in odds. This discovery broke the hearts of many great physicists. They had spent their lives believing the universe was a precise machine, and here it was, rolling dice at its very foundation. It felt like the ground had been pulled out from under all of science. If you cannot predict where a single particle will be, then the clockwork universe, the one we trusted for centuries, was never real at all. And I want to be clear, because this matters. This is not a fringe idea, or a wild theory, or something still being debated. This probabilistic nature of particles is one of the most tested, most confirmed facts in all of science. Every piece of modern technology you own, every computer chip, every phone, works precisely because this strange quantum behavior is real, and because we learn to predict its odds with breathtaking accuracy. We cannot say what a single particle will do, but we can predict the behavior of millions of them, statistically, well enough to build the entire modern world. So already, our first rule has fallen, certainty is gone. The universe runs on probability, but this is only the beginning of the strangeness. Because there is something even harder to accept waiting just ahead. It turns out that the simple act of looking at a particle, of measuring it, changes what it does. The observer, somehow, reaches into the experiment and alters reality itself. And that is where we go next. So now we come to the single strangest experiment in all of science. It is called the double slit experiment. And more than any other, it is the one that forces us to accept that reality is not what it seems. Here is the setup, and it is beautifully simple. You take a barrier with two thin, narrow slits cut into it, side by side. Behind that barrier, you place a screen that records wherever a particle strikes it, and then you fire tiny particles, one at a time, at the barrier, electrons, or single specks of light, and you watch where they land on the screen. Now think about what you would expect. Each particle goes through one slit or the other and lands on the screen behind it. So, after firing thousands of them, you should see two simple bands on the screen, one behind each slit. Two stripes. That is what common sense demands. But that is not what happens. Instead, the particles paint something impossible. They build up a pattern of many stripes, many bands of light and dark, spread across the whole screen. And this particular pattern has a name. It is called an interference pattern, and it is the unmistakable signature of waves. Let me explain why that is so shocking. When you drop two stones into a still pond, each sends out ripples, and where those ripples meet, they interfere. In some places, two crests add together and grow taller. In other places, a crest meets a trough and they cancel out to nothing. The result is a pattern of reinforced and cancelled waves. That is exactly the pattern the particles made on the screen, which means each particle was somehow behaving like a wave, passing through both slits at the same time and interfering with itself. Read that again. A single particle, fired alone, went through both slits at once and rippled against itself on the other side. One thing in two places at the same moment. Now, here is where it becomes truly unsettling. Naturally, scientists wanted to catch this in the act, so they placed a tiny detector at the slits, a little watcher, to see which slit each particle actually goes through. A simple, reasonable thing to do. Just look and settle the matter. But the moment they turned that detector on, everything changed. The instant the particles were being watched, they stopped behaving like waves. Each one suddenly went through just one slit, like a normal particle, and the interference pattern, all those beautiful stripes, simply vanished. The screen now showed just two plain bands, exactly what common sense had predicted all along. Sit with what this means. When no one is checking, the particle travels as a wave of possibility through both slits at once, but the instant it is observed, it is forced to choose. It collapses into a single, definite particle, taking one path. The simple act of looking changed what the particle did. Observation reached in and altered reality. And this is not a story or a thought experiment. This is a real result, performed countless times in laboratories all over the world for decades. It is one of the most reliably repeated experiments in the history of physics. Every time, the answer is the same. Watched, the particle acts one way, unwatched, it acts another. Now, I have to be honest and careful here, because this is the most misunderstood idea in all of quantum physics. When scientists say observation, they do not mean a human being consciously staring at the particle. They do not mean your mind has magic power over reality. Observation, here, means any physical interaction that measures the particle, any device that pulls information out of it. The detector does not need eyes, it only needs to interact. So please do not walk away thinking your gaze bends the universe. It is measurement itself, the act of extracting a definite answer that forces the particle to choose. That distinction matters, and I do not want to mislead you, but even with that honest correction, the mystery does not shrink. It deepens, because it leaves us with the most haunting question of all. If a particle only picks a single path at the moment it is measured, then what on earth was it doing before we looked? What state was it truly in when no one was measuring, when it was free to be a wave passing through both slits at once? The answer to that question has a name, and it is one of the strangest ideas the human mind has ever produced. That is where we go next. So what was the particle doing before we looked? The answer is a word you may have heard before, without knowing how strange it truly is: superposition. Superposition means that before it is measured, a particle is not in one state, waiting for us to discover which. It is genuinely in all of its possible states at the same time, not secretly in one and hidden from us, actually in all of them at once. Every possible position, every possible path, all reel together until the moment of measurement forces a single answer. I know that is hard to hold in your mind, so let me give you the closest picture we have. Think of a spinning coin. You flip a coin, and while it is still spinning in the air, whirling too fast to see, what is it? Is it heads? Is it tails? The honest answer is that it is neither, and in a sense, both. While it spins, it has no single, settled value. It is only when it lands, and you slap it down on the table, that it becomes one definite thing. Heads or tails, the spinning coin is a hint of superposition. The particle, before measurement, is like that coin, spinning through every possibility at once. And measurement is the hand that slaps it down and forces it to choose. Now, scientists needed a way to describe this strange, spinning cloud of possibilities with real mathematics. And they found one. They call it the wave function. The wave function is, in a sense, the truest description of a particle that exists. It is not a picture of where the particle is. It is a complete map of everywhere it could be and how likely each of those places is. It holds all the possibilities at once, every maybe, wrapped into a single mathematical object. And when you measure the particle, something dramatic happens to that wave function. In an instant, it collapses. All those spread out possibilities, all those maybes, suddenly snap down into one single reality. The many become one, the cloud becomes a point. Scientists call this the collapse of the wave function. One moment, the particle is everywhere it could be. The next, it is simply here. This whole picture, the superposition, the wave function, the collapse at measurement, has a name. It is called the Copenhagen interpretation. It was shaped in the 1920s, largely by two towering physicists, Niels Bohr and Werner Heisenberg. And for 100 years, it has been the standard way most physicists think about the quantum world. When you learn quantum mechanics in a university today, this is very often the picture you are taught first. But I want you to feel just how radical this idea really is. The Copenhagen interpretation says something almost unbelievable. It says that before you measure a particle, it does not have a definite position at all. Not a hidden one, not a secret one. It genuinely has no single location until the act of measurement brings one into being. Reality, in this view, is not sitting there fully formed, waiting for us to notice it. Reality, at the smallest scale, is unfinished, a haze of possibility, until something looks and forces it to settle. Think about how deeply that cuts against everything you know. You believe the world exists in a definite state, whether or not anyone is watching. The keys on your table are in one place, even when the room is dark and empty, and for big objects that is true, for reasons we will come to. But for a single particle, the Copenhagen interpretation says no. Its position is not real until it is measured. The measurement does not reveal the answer, the measurement creates it. This was the idea that so troubled Albert Einstein. This was the claim that made him ask whether the moon is really there when no one is looking. Because if a particle has no definite state until observed, then reality itself seems to depend on the act of observation. And to Einstein, that felt not just strange, but wrong, deeply, unacceptably wrong. We will come to his rebellion soon. But first, there is an obvious question you may already be asking. If tiny particles can be in many states at once, spinning through every possibility, then why not big things? Why not a chair, a car, a person? Why can't a large object be in two places at once? A physicist named Erwin Schrödinger asked exactly that question, and to expose how strange it all was, he imagined a cat. That is where we go next. So the physicist, Erwin Schrödinger, asked the obvious question. If particles can be in two states at once, where does that stop? And in 1935, he dreamed up a thought experiment so unsettling that it is still famous almost 100 years later. We call it Schrödinger's cat. Now, here is the twist that most people never hear. Schrödinger did not invent this to show how wonderful quantum mechanics was. He invented it to mock it. He thought the whole idea of superposition, taken seriously, led to something absurd. And he built this scenario to prove it. His cat was meant to be a joke at the theory's expense, and yet, unsettlingly, the joke refuses to go away. Here is the experiment he imagined. Picture a sealed steel box. Inside it, you place a living cat, and along with the cat, you place a tiny, cruel device. There is a single radioactive atom, a Geiger counter to detect if it decays, and a flask of poison. If the atom decays, the counter triggers, the poison is released, and the cat dies. If the atom does not decay, nothing happens, and the cat lives. Then you close the box and you wait. Now here is the crucial part. Whether that single atom decays is a pure quantum event, and a quantum event, as we have learned, is governed by superposition. Until it is measured, the atom is in a superposition of both decayed and not decayed at the same time. Both possibilities real together. But follow the logic. The atom is tied to the poison, and the poison is tied to the cat. So if the atom is in a superposition of decayed and not decayed, then the poison is both released and not released, and the cat is both dead and alive. At the same time, not one or the other, hidden from view. According to the strict quantum picture, the cat is genuinely both, a living and dead cat blurred together until someone opens the box and looks, and only in the instant of looking does the cat become one or the other. That was Schrödinger's point. He was saying, look how ridiculous this is. A cat both alive and dead? Everyone knows that is impossible. So surely something is wrong with a theory that leads us here. And he had put his finger on one of the deepest puzzles in all of physics. It is called the measurement problem, and it is simply this. Where, exactly, is the line? We know tiny particles live in superposition. We know large objects, like cats and tables and people, do not. You have never seen a cat that is both alive and dead. So somewhere between the single atom and the whole cat, the strange quantum rules must give way to the solid, everyday rules we know. But where? At what point does a fuzzy cloud of maybes become a single, definite fact? Nobody has ever found that exact line, and that missing line is one of the great unsolved mysteries of quantum physics. Now, let me be honest about where the science stands today, because it is genuinely astonishing. For a long time, superposition was thought to belong only to the tiniest things, single particles and atoms. But over the past few decades, scientists have pushed the boundary further and further. They have placed larger and larger objects into real superposition in the laboratory. Not just single particles, but groups of thousands of atoms. They have even taken a tiny metal object, just barely large enough to be seen with the naked eye, and placed it into a superposition of vibrating and not vibrating at once. No one has done this with a literal cat, and perhaps no one ever will. But the line, wherever it is, sits much further out than we once believed. So Schrödinger's joke has curdled into something serious. He meant to show the theory was absurd. Instead, the universe seems to have replied, "This absurdity is simply how I work, and I will show you how far it reaches." But all of this raises a question we have quietly skated past. We keep speaking of particles as though they are tiny objects, little specks and grains. But if a particle can be a wave and spread through both slits and hover in a haze of possibility, then what is a particle really? What is it actually made of? At the deepest level, the answer is perhaps the most beautiful idea in all of physics. And it says that particles, in truth, are not things at all. That is where we go next. So what is a particle really? The answer is perhaps the most beautiful and least known idea in all of physics. A particle is not a tiny thing. A particle is a ripple. Let me explain, because this changes the whole picture. Our best and deepest theory of reality says that the universe is not fundamentally made of little grains of matter. It is made of fields. Now, a field is a strange thing to imagine, so start with something familiar. Think of the surface of a still pond, flat, calm, stretching out in every direction. That surface exists everywhere across the pond, whether or not anything is happening to it. Now imagine that all of space, the entire universe, is filled with invisible fields like that. Not one field, but several, layered over each other, filling every corner of existence. There is a field for electrons, spread through all of space. There is a field for the particles of light. There is a field for every kind of particle that exists. These fields are the true fabric of reality. They are always there, everywhere, silent and unseen. And here is the beautiful part. What we call a particle is simply a ripple in one of these fields. Drop a pebble into that still pond, and a ripple races across the surface. That ripple is not a separate object you added to the pond. It is the pond itself, moving. In exactly the same way, an electron is a ripple in the electron field. A particle of light is a ripple in the field of light. The particle is not a thing sitting on top of the field. It is the field itself, vibrating. Matter, at its deepest level, is not stuff. It is motion in an invisible ocean that fills all of space. And this idea quietly solves a mystery you may never have thought to ask. Why is every electron in the universe exactly identical? Every single electron, everywhere, has precisely the same mass, the same charge, the same properties, with no variation at all. In the world of ordinary objects, no two things are ever perfectly the same. No two grains of sand, no two snowflakes. So why are all electrons perfect copies? Now you have the answer. They are all ripples in the very same field. They are identical for the same reason that every wave on one pond has the same nature. They are all made of the same underlying water. But the strangest consequence of this idea is what it tells us about empty space. Because if fields fill all of space and are always there, then even a perfect vacuum, a region with all the particles removed, is not truly empty. The fields are still there, and fields are restless. They are never perfectly still. So in what looks like total emptiness, the fields quietly tremble. And in those tiny trembles, particles flicker into existence and vanish again almost instantly. They are called virtual particles. Pairs of them appear out of the field, exist for the briefest flash of time, and disappear before they can ever be caught. Empty space is not empty at all. It is a boiling, fizzing sea, with particles constantly bubbling up and popping away, everywhere, all the time, even in the deepest void between the stars. Take that in. The emptiest place you can imagine, a perfect vacuum far out in deep space, is actually seething with activity. It is like the surface of a pond that looks perfectly still, but under a microscope is trembling with 1,000 tiny ripples. There is no such thing as true nothingness. Even nothing is full. And this is not a poetic flourish. We have measured the effects of these virtual particles in careful experiments with stunning precision. 2 metal plates, placed extremely close together in a vacuum, are gently pushed toward each other by this restless sea of appearing and vanishing particles. The pressure of nothingness is real, and we can feel it. The fizzing vacuum is not a metaphor, it is measured fact. So this is the true picture of reality. Not tiny solid balls, but a set of invisible fields filling everything, with particles as ripples dancing across them, and even empty space alive with fleeting, flickering motion. It is a far stranger and more beautiful universe than the one we imagine. But there is a final rule these ripples must obey. A deep, unbreakable limit on what we are ever allowed to know about them. It is one of the most famous ideas in all of science, and it is often badly misunderstood. It says that some things simply cannot be known, no matter how clever we are, and that is where we go next. So here is the final rule, and it is one of the most famous ideas in all of science. It is called Heisenberg's uncertainty principle, and it says something that sounds almost unfair. There are certain pairs of things about a particle that you can never know both of at the same time, no matter how good your equipment is. The most famous pair is this: a particle's position, where it is, and its momentum. which is really its motion, where it is going, and how fast. The uncertainty principle says you can never know both of these precisely at once. The more exactly you pin down where a particle is, the more hopelessly blurry its motion becomes. And the more exactly you measure its motion, the more its position smears into a haze. Pin down one, and the other slips away. You can never have both in sharp focus together. Let me give you a picture that captures this. Imagine trying to photograph a fan spinning at full speed. You have two choices. You could use a very fast shutter, freezing the motion, and you would get a crisp photo showing exactly where each blade is, frozen in place. But in that frozen image, you would have no idea how fast the fan is spinning. The motion is invisible. Or you could use a slow shutter and capture the blades as a smooth blur, which tells you clearly that it is spinning fast. But now you cannot say where any single blade actually is, position or motion. You can capture one clearly, but never both in the same photograph. The particle is like that spinning fan. Reality itself will only ever let you have one answer in focus. Now here is the part that almost everyone gets wrong, and I want to be very careful and honest about it. Most people assume the uncertainty principle is about clumsy measurement. They think it means that when you poke a particle to measure it, you accidentally disturb it, and that is why you cannot get both numbers. As if the problem is just that our tools are too heavy-handed. That explanation is easy to imagine, and it is wrong. The truth is far deeper and far stranger. The uncertainty is not caused by our clumsy measuring. It is built into the particle itself. The particle does not secretly have both a definite position and a definite motion that we are simply too clumsy to catch. It genuinely does not possess both at once. The two values do not exist together in sharp form at the same time at all. It is not that we cannot find the answer. It is that the answer is not there to be found. Reality, at this scale, simply refuses to hold both facts at once. This follows directly from everything we have already learned. Remember, a particle is not a solid dot. It is a spread out wave, a haze of possibility, and a wave is a slippery thing. If you squeeze a wave into a very sharp, narrow spike, so you know exactly where it is, then it loses any clear rhythm and its motion becomes meaningless. And if you stretch it into a long, smooth, regular wave, so its motion is perfectly clear, then it is spread across a wide region and its position is nowhere in particular. A wave simply cannot be both perfectly located and perfectly regular at the same time, and since particles are waves, they inherit this limit. The uncertainty is not a failure of our tools. It is the nature of what a particle is. Sit with how profound this is. There is a hard wall around what can be known about the universe. Not because we are not clever enough, not because our instruments are too crude, but because the universe itself does not contain that information in a definite form. There are facts that are not merely hidden from us. They simply do not exist until they are measured. Certainty, once again, dissolves, not in our minds, but in reality itself. And this was the final straw for one particular man. Because to Albert Einstein, all of this, the probability, the collapse, the fuzziness, the uncertainty, was simply intolerable. He could not accept a universe that runs on chance and refuses to hold definite facts. He famously protested that God does not play dice with the universe, and so Einstein set out to prove that the whole strange picture had to be incomplete, that there had to be a deeper hidden layer of reality underneath, one that was solid and certain after all. And in trying to prove it, he stumbled into the strangest phenomenon of all. That is where we go next. So Einstein set out to prove the whole strange picture was incomplete. And in the year 1935, together with two colleagues, Boris Podolsky and Nathan Rosen, he designed an argument meant to expose the flaw once and for all. But instead of breaking quantum mechanics, their argument uncovered the most bewildering phenomenon in all of physics. Today, we call it entanglement. Here is what entanglement means. You can create a pair of particles that are deeply linked, born together, connected in such a way that they behave as a single system, even after you separate them. And once they are linked like this, something astonishing follows. If you measure one particle and find it in a certain state, then the other particle is instantly forced into the matching state. At once, no matter how far apart they are, and I mean truly far apart. You could take one particle here and carry the other to the far side of the world, or to the far side of the galaxy, and the rule would still hold. Measure one, and its distant partner settles into its matching state in the very same instant. Not a second later, not after a signal has time to travel. Immediately, across any distance at all. Now, you should feel how impossible that sounds, because nothing in the universe is supposed to travel faster than light. If I measure a particle here, and its partner a billion miles away responds instantly, then somehow information appears to have crossed that gulf faster than any light beam ever could. It seemed to violate the deepest speed limit in all of nature. This is exactly what troubled Einstein. He gave it a name dripping with disbelief. He called it spooky action at a distance, and he was certain it could not be real. So Einstein offered a calmer, more sensible explanation, and it is genuinely a good one. He said, there is no spooky connection at all. The two particles simply agreed on their states in advance, at the moment they were created, and then carried those settled answers with them, like secret instructions all along. Let me give you the picture that makes his idea click. Imagine I take a pair of gloves, one left and one right. I put each into a separate box without looking, and I mail one box to you in another country, keeping the other with me. Now, the instant I open my box and find the left glove, I know immediately that yours must be the right glove. Instantly, across the whole world. But nothing spooky happened. No signal raced between the boxes. The gloves were simply always a left and a right from the very beginning. My opening the box did not change yours. It only revealed what was already fixed. That was Einstein's answer, he said. The particles are like those gloves. They are not in a fuzzy, undecided state at all. They secretly carry hidden information, settled from birth, and measuring one just reveals what was already true. Scientists call this the idea of hidden variables. If Einstein was right, then quantum mechanics was not the whole story. There was a deeper, hidden, perfectly ordinary layer of reality underneath, where everything was definite and certain, just as our common sense demands. So now there were two competing explanations, and they could not both be true. On one side stood the quantum picture. The particles are genuinely undecided, in a shared haze of possibility, until the moment one is measured, and then some real, instant, spooky connection settles them both. On the other side stood Einstein. There is no spooky connection. The particles carried hidden instructions all along, and measurement merely uncovers them. And here was the agonizing problem. For decades, these two explanations gave exactly the same predictions for every experiment anyone could think of. Whether the particles were undecided until measured or secretly settled from the start, the results looked identical. There seemed to be no possible test that could tell them apart. So the questions sat there, unanswered, for 30 years. One of the deepest questions about the nature of reality, and it looked as though it might be impossible to ever settle. It seemed doomed to remain forever, a matter of taste, of philosophy, of which story you simply preferred to believe. But then, in the 1960s, a quiet physicist from Northern Ireland did something that everyone had assumed was impossible. He found a way to put the question to the test. He designed an actual experiment that could reveal, once and for all, whether Einstein was right or whether the universe truly is as spooky as it seems. And that is where we go next. So in 1964, a quiet physicist named John Bell from Northern Ireland did something extraordinary. He found a way to settle the argument, not with philosophy, not with opinion, but with a real, testable experiment. It was one of the most brilliant ideas in the history of science, and it turned a question about the nature of reality into something you could actually measure in a laboratory. Here is the heart of what Bell realized. He worked out that Einstein's idea, the hidden gloves, the secret instructions carried from birth, made a specific prediction. If the particles really did carry settled answers all along, then when you measured many pairs of them, in many different ways, the results could only agree with each other up to a certain amount. There was a ceiling, a hard limit on how often the particles could match. Bell wrote down that limit as a precise number, and crucially, quantum mechanics predicted something different. It said that if the particles were truly undecided until measured, truly connected by that spooky link, then they would match more often than Einstein's ceiling allowed. They would break through the limit. Do you see the beauty of this? For the first time, the two ideas made different predictions. Einstein's hidden reality said the agreement must stay below a certain line. Quantum mechanics said it would cross that line. All anyone had to do now was build the experiment, measure thousands of entangled particles, and see which side won. The deepest question about reality had become a simple matter of counting, but building that experiment was fiendishly difficult. It took years. The first real attempt came in 1972 from a physicist named John Clauser, who managed the first true test of Bell's idea. Then, in 1982, a physicist named Albert Einstein performed a far more careful and convincing version, sealing off the loopholes that might have let Einstein's picture sneak through. And later, another physicist, Anton Zeilinger, pushed the experiments to new heights of precision, closing the remaining gaps one by one until there was nowhere left for doubt to hide. And what did they find? After all those thousands upon thousands of measurements, they found that the particles broke Einstein's limit every time. The agreement between them soared past the ceiling that hidden variables would have allowed and landed exactly where quantum mechanics said it would. The result was clear, and it has been confirmed over and over in the decades since. Einstein, the greatest mind of the age, was wrong. Let me say plainly what that means, because it is staggering. There are no hidden gloves. The particles do not carry secret, settled answers from birth. Before measurement, they genuinely are in that shared haze of possibility, undecided, connected across space by a link that Einstein himself could not stomach. When you measure one, its partner truly is affected instantly, no matter how far away it sits. The spooky action Einstein tried so hard to banish is simply real. Scientists have a careful phrase for what these experiments proved. They say the universe is not locally real. Let me unpack those two words, because each carries a shock. Real means that things have definite properties before you measure them, waiting to be found, and these experiments showed that is false. Local means that nothing can be affected instantly from far away, that distant objects cannot influence each other faster than light. And these experiments showed that is false too. One of those two comforting beliefs, and perhaps both, simply has to go. The universe refuses to be both real and local. It is one of the most profound discoveries humanity has ever made. And this was no small footnote. In the year 2022, John Clauser, Albert Einstein, and Anton Zeilinger were awarded the Nobel Prize in Physics for this work, for proving, beyond any doubt, that the strange, spooky, uncertain quantum picture is not a mistake, not an incomplete story, but the true nature of reality. Einstein's dream of a hidden, orderly world underneath was laid to rest. So we have finally arrived at solid ground. This much we know for certain. The universe is not locally real. Particles have no definite state until measured, and entanglement links them across any distance in a way that still defies our every instinct. But knowing this only sharpens the deepest question of all, the one we have been circling all night. If a particle has no definite reality until it is observed, then what is really happening out there when no one is looking? What is the true nature of a reality like this? And here, at the very edge of human knowledge, the answers become stranger than anything yet. That is where we end. So we know for certain that reality is not what it seems. A particle has no definite state until it is measured, but this leaves the ultimate question. If the answer is not decided until we look, then what is truly happening when no one is looking? And here, at the very edge of human knowledge, physicists genuinely disagree. There are several possible answers. I want to walk you through the three most striking, and be honest that not one of them is proven. The first is the Copenhagen view we have already met. It says, quite simply, do not ask. The particle is a haze of possibility, and when you measure it, that haze collapses into one reality. The unmeasured world has no definite state, and the question of what it is doing when unwatched may have no answer at all. The second answer is far bolder. It is called the many worlds interpretation, proposed by a physicist named Hugh Everett in 1957. Everett said, the haze never collapses at all. Instead, every possibility becomes real, each in its own separate universe. When you measure a particle that could be here or there, the universe simply splits. In one universe, you find it here. In another, equally real universe, another version of you finds it there. Every quantum event, everywhere, is constantly branching reality into countless copies. If this is true, there are unimaginably many universes and countless versions of you living out every choice you did not make. It sounds like madness, and yet serious physicists take it seriously because the mathematics allows it. The third answer says Einstein was not entirely wrong. It suggests there really is a hidden layer after all, an invisible guiding wave that steers each particle along a definite path, so the particle always has a real position, quietly directed by this deeper wave. It restores some of the solid reality Einstein longed for, though at a strange cost. Now here is the maddening, honest truth. These three pictures, and others besides, all predict exactly the same experimental results. Every test we can perform gives the same answer, no matter which interpretation is true. So, we have no way, at least for now, to tell which one describes reality. It is like having three different maps of the same city, each drawn in a completely different style, yet each guiding you perfectly to your destination. The maps disagree about what the city truly looks like, but you can never catch any of them being wrong. Which map shows the real city? We simply cannot say, but there is one more idea, and it may be the most profound of all. A growing number of physicists have started to wonder whether we have been asking the wrong question all along. We keep asking what a particle is doing when no one observes it. But what if that question has no meaning? What if there is no such thing as a lonely, observer-free reality, sitting out there, fully formed, waiting to be seen? In this view, the properties of the world do not exist on their own. They come into being only in the relationship between the observer and the observed. Reality is not a collection of objects with fixed properties. It is a web of interactions in which nothing is fully real on its own. You are not standing outside the universe, peering in like a viewer at a painting. You are woven into it. Every time you observe the world, you are not simply discovering what is already there. In some small, real way, you are taking part in bringing it into being. Sit with that on this quiet night. The old picture had you as a tiny spectator, lost in a vast machine that would grind on exactly the same whether you existed or not. But the deepest reading of quantum physics whispers something stranger and far more intimate, that the universe is not a finished thing you are trapped inside. It is an ongoing process that you are part of. Reality and the mind that observes it may be two sides of a single, unfinished act. We began tonight with a simple magic box, and we end with the discovery that the whole universe may be a little like that box, shimmering with possibility, becoming real in the presence of those who look. You are not a stranger here. You are part of how the cosmos comes to know itself. Thank you for wandering to the edge of reality with me tonight. If it left you seeing the world a little differently, share it with someone who loves the deepest questions. And if you would like to keep exploring them with us every Wednesday and Sunday, you know what to do. Until the next journey, rest well, keep wondering, and never stop looking up.